So, I wanted to start a series where I read research papers and try to teach myself and understand them out loud as I go. So, I'm mainly here to work this out for myself and improve my own understanding, but you can work this out with me if you want. So, the first paper I'm reading is the word2vec paper from 2013. It's a pretty well known one in machine learning. The main claim basically is that you can turn words into lists of numbers in a way where the numbers carry meaning, to the point where you can do arithmetic with these words. Like, for example, king minus man plus woman should land somewhere near queen. So, we are going to see how that works. Authors of this paper are Thomas Mikolov, Ilya Sutskever, Chen, Greg Corrado, and Jeffrey Dean. So, distributed representations of words and phrases and their compositionality. So, two words in the title. Distributed representation means that instead of giving a word a single identification, you are spreading its meaning across a whole list of numbers, and each number holds a little bit of it. So, no single number has a designated meaning. The meaning is spread out across all of them. And then compositionality is the question of whether you can combine the numbers for two different words to get the pair. So, for example, this is an example given in the abstract, but can Air plus Canada give you Air Canada? So we will get back to this later. So first, let's read the abstract. The recently introduced continuous skip-gram model is an efficient method for learning high-quality distributed vector representations that capture a large number of precise syntactic and semantic word relationships. In this paper, we present several extensions that improve both the quality of vectors and the training speed. By subsampling of the frequent words, we obtain significant speedup and also learn more regular word representations. We also describe a simple alternative to the hierarchical softmax called negative sampling. So let's go through the words that they're throwing at us in this first paragraph. Skip-gram model is the model itself, the thing that learns the word numbers. Subsampling, which they say gives a speed up and better vectors. I'll guess it means ignoring some of the data, but we will see. Hierarchical softmax, which I have no read on yet, so we're going to leave this blank for now. And then negative sampling, which they call a simple alternative to hierarchical softmax. So basically a shortcut for this. So this is the model. Here are the tricks to make it faster and better. And that's the entire shape of this paper basically. Now, an inherent limitation of word representations is their indifference to words, word order, and their inability to represent idiomatic phrases. For example, the meanings of Canada and air cannot be easily combined to obtain Air Canada. Motivated by this example, we present a simple method for finding phrases in a text and show that learning good vector representations for millions of phrases is possible. So here is the limitation that they point out. Word numbers don't handle phrases well. Air Canada isn't Air plus Canada, it's an airline. So part of the paper is a way to deal with phrases like this. Alright, so now we have a map of what this paper is about. Let's read the introduction. Distributed representations of words in a vector space help learning algorithms to achieve better performance in natural language processing tasks by grouping similar words. One of the earliest use of word representations date back to 1987 due to Rumelhart, Hinton, and Williams. This idea has been applied to statistical language modeling with considerable success. The following up work includes applications to automatic speech recognitions and machine translation, and a wide range of NLP tasks. So this paragraph explains why you should care. Representing words as vectors is an old idea that has been traced back to the 1980s. The point is basically that when you group similar words together in a number space, learning algorithms do better at language tasks. Recently, Mikolov et al. Introduced the skipgram model, an efficient method for learning high quality representations of words from large amounts of unstructured text data. Unlike most of the previously used neural network architectures for learning word vectors, training of the skipgram model does not involve dense matrix multiplications. So, this is important. This makes the training extremely efficient, and an optimized single machine implementation can train on more than 100 billion words in one day. So the two things that they are pointing out here is that first, the model is cheap to run. It skips like extremely heavy math that older neural networks needed. Second, because it's cheap, they can train it on a huge amount of text, over 100 billion words in a day. So this is part of why this model works. The word representations computed using neural networks are very interesting because the learned vectors explicitly encode many linguistic regularities and patterns. Somewhat surprisingly, many of these patterns can be represented as linear translations. For example, the result of a vector calculation, Madrid minus Spain plus France, is closer to the vector Paris than any other word vector. So they've basically mentioned this method, stated in plain words. If you take the arrow for Madrid, subtract Spain, and then add the arrow of France, you land close to Paris. So they're saying the relationship of is the capital of became a consistent direction that you can actually move in. So if you subtract Spain from Madrid, it leaves something like the capital. And then adding France to it points to France's capital, which is Paris. In this paper, we present several extensions of the original skipgram model. We show that subsampling of frequent words during training results in a significant speedup, around 2 to 10 times, and improves accuracy of the representations of less frequent words. In addition, we present a simplified variant of noise contrastive estimation for training the skipgram model that results in a faster training and better vector representations for frequent words compared to more complex hierarchical softmax that was used in the prior work. Word representations are limited by their inability to represent idiomatic phrases that are not compositions of the individual words. For example, Boston Globe is a newsletter, and so it is not a natural combination of the meanings of Boston and of globe. Therefore, using vectors to represent the whole phrases makes the skipgram model considerably more expressive. Other techniques that aim to represent meaning of sentences by composing the word vectors, such as the recursive autoencoders, would also benefit from using phrase vectors instead of the word vectors. The extension from word-based to phrase-based models is relatively simple. First, we identify a large number of phrases using the data-driven approach, and then we treat the phrases as individual tokens during the training. To evaluate the quality of the phrase vectors, we developed a test set of analogical reasoning tasks that contain both the words and phrases. A typical analogy pair from our test set is Montreal, Montreal Canadiens, Toronto, Toronto Maple Leafs. It is considered to have been answered correctly if the nearest representations to the vector Montreal Canadiens minus vector Montreal plus vector Toronto is vector Toronto Maple Leafs. Finally, we describe another interesting property of the skipgram model. We found that simple vector addition can often produce meaningful results. For example, vector Russia plus river is close to vector Volga River, and Germany plus capital is close to the vector Berlin. This compositionality suggests that a non-obvious degree of language understanding can be obtained by using basic mathematical operations on the word vector representations. So let's go to the diagram here, and it basically depicts the actual idea of what this model is. So there's this one word in the middle that they call WT. This means a word at the position T. These arrows point out to its neighbors, 2 words before WT and 2 words after. So the model's job is, given this middle word, guess the words around it. That is skipgram. You give it France and it should expect something like Paris or Europe or country. So that is what this model is basically about. So the skipgram model. The training objective of the skipgram model is to find word representations that are useful for predicting the surrounding words in a sentence or a document. More formally, given a sequence of training words, W1, W2, etc., the objective of the skipgram model is to maximize the average log probability. So this sum looks like a lot, but basically, let's only read the inside bit. Log P of WT plus J given WT. So in plain words, this is the probability of a neighbor word given the center word. So the model wants this value to be high. All these sum signs around it just say, do this for every single center word inside the text, for every single neighbor around it, and then average it. So the whole goal of training is to make the real neighbors come out as likely as possible. Here, C is the size of the training context, which can be a function of the center word WT. Larger C results in more training examples and thus can lead to a higher accuracy at the expense of training time. The basic skipgram formulate defines P of WT plus J given WT using the softmax function. So first, here, C is the window size. It basically tells you how many words on each side counts as neighbors. A bigger window means that there are more neighbors to predict, which they say gives you better quality, but it runs slower. So there is a speed versus quality dial, and this is one of them. Now the second equation, softmax function. So how do you actually compute the probability? That is softmax. So let's split the fraction into top and bottom. So the top is a dot product between two word vectors. So a dot product is basically how aligned are these two arrows, and they are scored high if they point the same way. So the top is basically how well the center word matches a candidate neighbor. And the bottom is basically the same exact thing, but computed for every single word in the vocabulary, and then it's added up. So dividing this by the total is what turns these scores into proper probabilities that add up to 1. And so this bottom part is the problem. VW and V-W are the input and output vector representations of W, and big W is the number of words in the vocabulary. This formulation is impractical because the cost of computing this is proportional to big W, which is often large, 10 raised to 5 to 10 raised to 7 terms. So this is basically saying the cost is proportional to the size of the dictionary, which could be up to millions of words. So the bottom of this fraction basically makes you loop over the whole dictionary every time you want to process one single word. So if the dictionary has a few million words, that's millions of operations per word done billions of times. This just doesn't scale in the real world. So this section 2 will tell us different tricks to avoid computing this bottom sum. And this is the problem that they are solving here. So hierarchical softmax. The problem again is that they are computing over the whole dictionary, and the first trick to avoid it is called hierarchical softmax. So let's read it and try to get an idea of what it is. The hierarchical softmax uses a binary tree representation of the output layer with the W words as its leaves. For each node explicitly represents the relative probabilities of its child nodes. These define a random walk that assigns probabilities to words. More precisely, each word W can be reached by an appropriate path from the root of the tree. Let NWJ be the jth node of the path from the root to W, and LW be the length of this path. So NW1 is equal to root, and LW is equal to W. So in addition, for any inner node N, let CHN be an arbitrary fixed child of N, and let this be 1 if X is true and -1 otherwise. Then the hierarchical softmax defines P W0 given W1 as follows. So the idea in plain words is basically, instead of a flat list of million words, you arrange all the words as the leaves at the bottom of a tree. And at each fork you go left or right, and the number of forks you pass is around the log of the dictionary size. So for a million words, instead of a million checks, it's only about 20. So you've basically made a much shorter path instead of just checking every single one. So this equation here is the bookkeeping for that walk. So at each fork, it works out the chance of going left versus right, and then it multiplies them across the path. So I'm not gonna go through this notation, but the part that matters is basically it does a short walk instead of a full scan. The structure of the tree used by the hierarchical softmax has a considerable effect on the performance. Nian Hinton, sorry if I pronounced the name wrong, explored a number of methods for constructing the tree structure and the Huffman tree, as it assigns short codes to the frequent words, which results in fast training. It has been observed that before that, grouping words together by their frequency works well as a very simple speed-up technique for the neural network-based language models. So, one detail worth noting is here, Huffman tree. So they build the tree so that common words sit closer to the top, which is what a Huffman tree does. So the words that you run into all the time has the shortest paths, which makes training even faster. So that was like a very nice, sensible touch. Now, section 2, negative sampling. So this is the second trick, and this is the one that this paper is famous for. It's the same problem, but it avoids the giant sum, and the approach is a lot simpler. So an alternative to the hierarchical softmax is noise contrastive estimation, which was introduced by Gutman and Hyvarinen and applied to language modeling by Nian Te. NCE posits that a good model should be able to differentiate data from noise by means of logistic regression. This is similar to hinge loss used by Collibert and Weston, who trained the models by ranking the data above noise. While NCE can be shown to approximately maximize the log probability of the softmax, the skip-gram model is only concerned with learning high-quality vector representations. So we are free to simplify NCE as long as the vector representations retain their quality. We define negative sampling NEG by this objective. Okay, so they start from something called noise contrastive estimation, or NCE. And then they say they don't need the full version, they just simplify it. So the simpler version of NCE is negative sampling. So setting this formula aside for a second, the question was, out of 1 million neighbors, how likely is this one neighbor? So that is extremely expensive to compute. So they swap out this for an easy yes or no logic. So if you take a pair, a center word and a word that actually shows up next to it, and then tell the model that yes, this is a real pair, please score it high. And then you grab a handful of random words that probably don't show up next to it, which they call negative samples, and then they tell the model, these ones are fake, please score them low. So that's the whole thing. This pushes the real pair up and pushes the fake ones down. So the reason this helps is that you don't have to use the whole million word dictionary every time. You're only touching a few words at every single step. So the only real neighbor and your handful of fakes is used instead of the entire million word dictionary. The giant sum is entirely gone, and instead of ranking one word against every word, you are just like using one word and letting them beat a bunch of random imposters. So in this equation here, sigmoid, okay, so in this equation, that sigmoid is a squashing function that turns any score into a number between 0 and 1. The first term pushes the real pair's confidence up, and the sum pushes k fake pairs' confidence down. And k is how many fake pairs you grab per real pair. So we define negative sampling by the objective, which is used to replace every log p w naught given wi term by skipping in the skip gram objective. Thus the task is to distinguish the real world w naught from draws from the noise distribution p and w using logistic regression where there are k negative samples for each data sample. Our experiments indicate that values of k in the range 5 to 20 are useful for small training datasets, while for large datasets, k can be as small as 2 to 5. The main difference between the negative sampling and the NCE is that NCE needs both samples and the numeric probabilities of the noise distribution, while negative sampling only uses samples. While NCE approximately maximizes the log probability of the softmax, this property is not important for our application. So they basically give you the settings. 5 to 20 are useful for small data sets, and 2 to 5 for large ones. So both NCE and NEG have the noise distribution as a free parameter. We investigated a number of choices for P and W and found that the unigram distribution U of W raised to the 3 by 4th power outperformed significantly the unigram and the uniform distributions for both NCE and NEG on every task we tried, including language modeling. So this last paragraph, how do you pick the random fake words? It's not evenly, and it's purely by how common they are. So they raise each word's frequency to the power 3/4 first. This is just a number that worked out the best for them, and it has no other meaning behind it. The effect is that it gives rarer words a slightly better chance of getting picked as a fake. So you don't need to know what exactly 3/4 is. Even they basically said they just tried a few options and 3/4 won, but it's worth knowing. So subsampling of frequent words. In very large corpora, the most frequent words can easily occur hundreds of millions of times. Examples in, the, and a. Such words usually provide less information value than the rare words. For example, while the skipgram model benefits from observing the co-occurrences of France and Paris, it benefits much less from observing the frequent co-occurrences of France and the, as nearly every word co-occurs frequently within a sentence with the. This idea can also be applied in the opposite direction. The vector representations of frequent words do not change significantly after the training on several million examples. So this one is pretty straightforward. Words like a, the, and in show up everywhere and tell you almost nothing about the actual meaning. The model learns a lot from seeing like France next to Paris, but almost nothing from seeing France next to the, because everything sits next to the. So there is no point spending so much time on it. To counter the imbalance between the rare and frequent words, we use a simple subsampling approach. Each word's WI in the training set is discarded with probability computed by this formula. So the fix is formula, where FWI is the frequency of word WI and T is a chosen threshold, typically around 10 raised to minus 5. We chose this subsampling formula because it aggressively subsamples words whose frequency is greater than T while preserving the ranking of the frequencies. Although this subsampling formula was chosen heuristically, we found it to work well in practice. It accelerates learning and even significantly improves the accuracy of the learned vectors of the rare words, as will be shown in the following sections. So, basically what they've done is, they've thrown away some words during the training, and the more common a word is, the more likely it is to get dropped on any given appearance. So this equation is just the formula for that drop probability. So higher frequency means a higher chance of skipping it. And so this threshold is around 1 in 100,000. So that controls how aggressive this is. And so, as described, the payoff is like two different things at once. It's a huge speed up, and rare words actually come out better because the model isn't constantly buried in words like the and a, and you can pay more attention to the words that actually matter. The second part is that throwing away data actually made it better, not just faster. So, empirical results. In this section, we evaluate hierarchical softmax, noise contrastive estimation, negative sampling, and the subsampling of the training words. We used analogical reasoning task introduced by Mikolov et.al. The task consists of analogies such as Germany, Berlin, France, ? Which are solved by finding a vector x, such as vector x is closest to the vector Berlin minus vector Germany, plus vector France. According to the cosine distance, we discard the input words from search. This specific example is considered to have been answered quickly. This specific example is considered to have been answered correctly if x is Paris. The task has two broad categories: the syntactic analogies such as quick, quickly, slow, slowly, and the semantic analogies such as the country to capital city relationship. So here is how they test whether the vectors are actually good. So to answer this question, if Germany is to Berlin as France is to what? You do the vector math. So Berlin minus Germany plus France, and then see which word the result lands closest to. If it's Paris, then they got it right. The cosine distance thing they mentioned is just a measure of which arrow is closest in that direction. For training the skipgram models, we have used a large data set consisting of various news articles, an internal Google dataset with 1 billion words. We discarded from the vocabulary all words that occurred less than 5 times in the training data, which resulted in a vocabulary of size 692,000. The performance of various skipgram models on the word analogy test set is reported in the first table. The table shows that a negative sampling outperforms the hierarchical softmax on the analogical reasoning task and has even slightly better performance than the noise contrastive estimation. The subsampling of the frequent words improves the training speed several times and makes the word representations significantly more accurate. So let's scroll to table 1. So each row is a different method, and the last column is the overall accuracy score for that method. So one thing that you'd notice is that the negative sampling, which is the simple yes or no trick, it beats the tree method, hierarchical softmax, and NCE as well. And if you look at the second block, which is subsampling, the times get roughly cut in half and the accuracy has gone up as well. So both of these tricks are pulling their weight, and it's visible on this table. So now let's go down to learning phrases. As discussed earlier, many phrases have a meaning that is not a simple composition of the meanings of its individual words. To learn vector representation for phrases, we first find words that appear frequently together and infrequently in other contexts. For example, New York Times and Toronto Maple Leafs are replaced by unique tokens in the training data, while a bigram "this is" will remain unchanged. So let's go back to one of the previous examples, Boston Globe. Boston Globe is a newspaper. It's not Boston plus Globe. So if you only ever have single word vectors, you can't capture it. So the fix here is pretty direct. They treat the phrase as one word. So they basically, in the previous example, they glue Boston and Globe into a single token and learn one vector for the whole phrase Boston Globe. So here, this way we can form many reasonable phrases without greatly increasing the size of the vocabulary. In theory, we can train the skipgram model using all n-grams, but that would be too memory intensive. Many techniques have been previously developed to identify phrases in the text. However, it is out of scope of our work to compare them. We decided to use a simple data-driven approach where phrases are formed based on the unigram and bigram counts using this formula. The delta is used as a discounting coefficient and prevents too many phrases consisting of very infrequent words to be formed. The bigrams with scores above the chosen threshold are then used as phrases. Typically, we run 2 to 4 phrases over the training data with decreasing threshold value, allowing longer phrases that consist of several words to be formed. We evaluate the quality of the phrase representations using a new analogical reasoning task that involves phrases. Table 2 shows examples of the 5 categories of analogies used in this task. The dataset is publicly available on the web. Alright, so basically, this is saying you can't just glue every pair of words together or the vocabulary, it blows up. So they have to score pairs. So they score it based off of how often do these two words show up together versus how often they show up separately. So pairs that go together a lot, like New York or Toronto Maple Leafs, they score high and get glued together. Pairs like "this is," which are just common words that happen to be next to each other, they score low and they stay apart. So the little delta in the formula here is a guard so that you don't glue together two rare words that happen to appear next to each other once. So they run this a few times just to loosen the threshold at each pass. So 2-word phrases can build up into 3 and 4-word phrases. And that's how you would get something like San Jose Mercury News, for example. Alright, so if we go to table 2, let's say New York Times, Boston Bruins, Detroit Pistons. So these are phrase analogies. It's like the same thing as before, but with phrases instead of just words. So New York is to New York Times as Baltimore is to Baltimore Sun. And their best model gets 72% on this data set, which is pretty good for thousands and thousands of phrases. The results of this, starting with the same news data as the previous experiments, we first constructed the phrase-based training corpus, and we trained several skipgram models using the different hyperparameters. As before, we used vector dimensionality 300 and context size 5. This setting already achieves good performance on the phrase dataset and allowed us to quickly compare the negative sampling and hierarchical softmax, both with and without subsampling of the frequent tokens. The results are summarized in Table 3. The results show that while negative sampling achieves a respectable accuracy even with k is equal to 5, using k equal 15 achieves considerably better performance. Surprisingly, while we found that the hierarchical softmax to achieve lower performance when trained without subsampling, it became the best performing method when we downsampled the frequent words. This shows that the subsampling can result in faster training and can also improve accuracy, at least in some cases. So, Table 3. So this is surprising. The hierarchical softmax method, which is the tree method, it was the worst without subsampling, but it became the best after using subsampling. So the combination of these tricks is what makes this model better. Now, Table 4. These are just examples showing the phrase vectors and how they land near sensible things. Okay. Additive compositionality. We demonstrated that words and phrase representations learned by the skipgram model exhibit a linear structure that makes it possible to perform precise analogical reasoning using simple vector arithmetics. Interestingly, we found that these skipgram representations exhibit another kind of linear structure that makes it possible to meaningfully combine words by an element-wise addition of their vector representations. This phenomenon is illustrated in Table 5. The additive property of the vectors can be explained by inspecting the training objective. The word vectors are in a linear relationship with the inputs of the softmax nonlinearity. As the word vectors are trained to predict the surrounding words in the sentence, the vectors can be seen as representing the distribution of the context in which a word appears. These values are related logarithmically to the probabilities computed by the output layer, so the sum of the two vectors is related to the product of the two context distribution. The product works here as the AND function. Words that are assigned high probabilities by both word vectors will have a high probability, and the other words will have a low probability. So if Volga River appears frequently in the same sentence together with the words Russian and river, the sum of these two word vectors will result in such a feature vector that is close to the vector of Volga River. So their explanation basically is, think of a word's vector as standing in for the kinds of context that the word actually shows up in. So when you add two vectors, it ends up working like the AND function. So you get words that fit the context of both inputs. So Russia brings in Russia-ish context, river brings in river-ish context, and the things that both Russian and river is Volga. So you don't have to fully understand the math, and it's interesting that this actually works. So comparison to published word representations. Many authors who previously worked on the neural network-based representations of words have published their resulting models for further use and comparison. Amongst the most well-known are authors Colbert and Weston Turian et al. And Nian Hinton. We downloaded their word vectors from the web. Mikolov et al. Have already evaluated these word representations on the word analogy task, where the skipgram models achieved the best performance with a huge margin. To give more insight into the difference of quality of the learned vectors, we provide empirical comparison by showing the nearest neighbors of infrequent words. These examples show that the big skipgram model trained on a large corpus visibility outperforms all the other models in the quality of the learned representations. This can be attributed in part to the fact that this model has been trained on about 30 billion words, which is about 2 to 3 orders of magnitude more data than the typical size used in the prior work. Interestingly, although the training set is much larger, the training time for the skipgram model is just a fraction of the time complexity required by the previous model architectures. So this is the comparison table. It takes some of the famous earlier word vector models and line up the nearest neighbors each one gives for some tricky words. So the older models often have blank cells, which means the word wasn't even in their vocabulary, and the neighbors are much messier. So the skipgram model is trained on tens of billions of words, so it gives clean and sensible neighbors. And their own read on why is mostly that they trained on about 100 times more data and they still ran faster. So this goes back to the theme of the first page, that a big part of what makes this better is the scale it can be used in. So the conclusion. The work has several key contributions. We show how to train distributed representations of words and phrases with the skipgram model and demonstrate that these representations exhibit linear structure that makes precise analogical reasoning possible. The techniques introduced in this paper can also be used for training the continuous bag of words model introduced. We successfully trained models on several orders of magnitude more data than the previously published models thanks to the computationally efficient model architecture. This results in a great improvement in the quality of the learned word and phrase representations, especially for the rare entities. We also found that the subsampling of the frequent words result in both faster training and significantly better representations of uncommon words. Another contribution of our paper is the negative sampling algorithm, which is extremely simple training method that learns accurate representations, especially for frequent words. Negative sampling. So the choice of training algorithm and the hyperparameter selection is a task-specific decision. As we found that different problems have different optimal hyperparameter configurations, in our experiments, the most crucial decisions that affect the performance are the choice of the model architecture, the size of the vectors, the subsampling rate, and the size of the training window. A very interesting result of this work is that the word vectors can be somewhat meaningfully combined using just simple vector addition. Another approach for learning representations of phrases presented in this paper is to simply represent the phrases with a single token. Combination of these two approaches give powerful yet simple way how to represent longer pieces of text while having minimal computational complexity. Our work can thus be seen as a complementary to the existing approach that attempts to represent phrases using recursive matrix vector operations. We made the code for training the word and phrase vectors based on techniques described in this paper available as an open source project. So basically, let's recap. There's a model, skipgram, that learns word vectors by trying to predict each word's neighbors. The way to compute this is slow because it loops over the entire dictionary, so we have learned shortcuts. The first is hierarchical softmax and then negative sampling, which turns hierarchical softmax into a more condensed version by just beating with a few random fake words instead of using the entire dictionary. So subsampling throws away overly common words and makes it both faster and better. So the resulting vectors have a straight line structure. So analogies work as subtraction and even plain addition of vectors, meaning something. The resulting vectors have a straight line structure, meaning that analogies work as subtraction and even plain addition of vectors mean something. And you can glue phrases into single tokens to handle things like Air Canada or New York Times. They also note that the best setting depends on the actual task. You have to tune it accordingly. Okay, so that's the whole paper. And a quick reflection. I thought that the math would be way more intimidating than it actually was. But it was quite intuitive and easy to just understand in like plain English. Um, Most of the math that scared me on the first read was just one single problem in disguise, like the dictionary being too big to loop over, and the rest was just clever ways around that first problem. And so, knowing that made the paper a lot easier to read. And a lot of the specific choices, like using 3/4 of the power, were just things that they tried because it worked better than everything else. It had no deep reason given, and I found that like quite reassuring. Um, but yeah, if I got something wrong, please let me know, and I will be continuing this series more for myself. And the next paper I will be reading is probably Attention is All You Need.